Hi everyone, we are starting Unit 7 today, all about right triangle trigonometry. Now, right triangles you are familiar with, of course, but trigonometry, just to let you know, means the study of triangles, specifically how their angles kind of match up, mix up, can help us determine the sides. So in the past, we've always had to use sides to find other sides and angles to find other angles. But now we're going to have some ways to mix and match. We'll be able to use sides to find angles and angles to find sides, and it'll just give us a lot more flexibility with what we're able to do with limited information. Today specifically, we're looking at how to apply the Pythagorean Theorem. Now some of this will be review, hopefully, and some of it will be new. So we'll just see how it goes. Remember, you can always email me to ask me any questions. More on that at the end. So our goals today, we're going to review Pythagorean Theorem. Hopefully that is review for you. We'll use Pythagorean Theorem to find missing lengths and talk about some of the trickier ones and how to not fall for those tricks. And then we're going to use the converse of the Pythagorean Theorem to test for rightness of triangles. So first thing I want you to do is just pause the video and use the Pythagorean Theorem to find AB. If you've got your PDF, or there were 3 people who picked up the paper copy from me yesterday. But if you want to use scratch paper, or if you have the PDF working, or if you printed it or whatever, we're going to try to use the Pythagorean Theorem to find this missing side AB. Pause the video and then come back once you have your answer. All right, I hope that you really did pause and take a minute to get your answer, because with these distance learning things, you really get out of it whatever you put in. If you just set the video to play while you're doing something else, if you keep the volume off, obviously that's bad news. So the more effort you put into trying to actually follow these and do it for yourself, the easier things will be when we get back on Wednesday. So hopefully you have an answer. But on the PDF or the paper, I asked you to find the exact value. Now, I want you to ask yourself, is the number you circled as your answer actually the exact value? Now, you might not even know. You don't know what I mean by exact value. So that's what we're going to talk about now real quick. Exact answers represent the full value of the solution with no little bits cut off. Basically, it means no rounding at all. So the most famous example of a situation where this comes up is with pi. Now, all through middle school and even your freshman year and whatever other classes you've had, typically when you've had to use pi, you were using 4-function calculators that didn't have a pi button. So they said, hey, use 3.14. But guess what? 3.14 is not an exact value for pi. Now that one you probably realized you were using an approximate version. But even if you add some more decimals, 3.14159, it's more precise, it's closer to the exact value, but still not the exact value. It actually doesn't matter how many decimals you try to put into your number, how precise you try to be. If you're trying to write out this decimal, you are never going to have an exact value for pi, because that decimal keeps going on forever. You could keep writing decimal places for the rest of your life and still not be done. So instead of trying to write out the decimal, you have to use the symbol. So that Greek letter is the representation of the exact value. Now, your calculators, the scientific calculators that some of you purchased, the ones that we have in class, those have a pi button, and they are programmed with enough decimals that obviously your calculator can't actually store the full value, but it's got enough decimals that it's never going to affect, the little bit that's been cut off will never affect your actual calculations. But when you're writing your answers, if I say write the exact answer, you have to use this symbol or it's a rounded answer. Now, square roots work a lot the same way. Because if the radicand, that number underneath the square root sign, if that's not a perfect square, then the number is irrational. It turns out to be a decimal that goes on forever and ever and ever. So to be exact with a square root answer, if it's not a perfect square, you have to actually use the symbol. And if you are working from the PDF, that's what fills in your blank there above the Pythagorean Theorem box. You need the word symbol. So to look back at the do now, we know, so maybe you know, hopefully this was a review of Pythagorean Theorem. So a squared plus b squared equals c squared is the equation that we get from that. Once you fill in the numbers, we were looking for the hypotenuse, which means we are looking for the c value. We had the two legs, so we had the a and the b. We plugged those in. 4 squared plus 8 squared equals c squared. If you did write out some work for this, please check the step-by-step. Make sure that you've got everything squared away because we're going to be using Pythagorean Theorem a lot. I want to make sure that you've got it all set. All right, next thing to do is evaluate those squares. 4 squared is 16, 8 squared is 64. Then we go ahead and add them up. We get 80, but that's all still equal to c squared. We don't want c squared. We want the plain old c. So to get rid of the squared, we use the inverse operation, square root. We'll square root both sides. It'll cancel the squared on the right, giving us plain old c, and square root of 80 on the left. And then as you were working on your do now task, if you got this far, you probably got out a calculator, you got on Desmos, maybe even your phone, and said, okay, what's the square root of 80? And you got 8.9. But 8.9 was a rounded answer. We don't want the 8.9. We want the square root of 80. That's the exact version. So what we're doing today, we're kind of doing a deep dive into Pythagorean Theorem. So even if you did remember that it was a squared plus b squared equals c squared, technically that's not the theorem, that's the equation that the theorem gives us. Now we'll use that equation quite a bit today, but I want you to actually have the Pythagorean Theorem in your notes. So this is an if-then theorem like we have been doing all year. So if a triangle is a right triangle, that's the first blank, that's our setup. Pythagorean Theorem only works on right triangles. Then here's our next phrase. I want you to pay attention. This next part, before the word equal, you see the word equal about 2/3 of the way down. This next phrase with two blanks in it, this is going to be our left side of that Pythagorean equation. So the sum means that you've added two things. So the sum, we know there's an addition in Pythagorean Theorem. Think about what gets added on that left side. It's a squared and b squared, right? So it's the sum of the squares, right? We've got two things that are squared, but the a and the b represent the lengths of the legs. So this first part, the sum of the squares of the lengths of the legs, that's a squared plus b squared. And that's equal to, well, in our equation, it says c squared, which is, c is the length of the hypotenuse. C squared would be the square of the length of the hypotenuse. So I want you to have that written down in your notes because the equation, yes, it's true when we have a right triangle, but the theorem itself, the way that it's worded, gives us a little more flexibility and a little more awareness of what's happening and gives us a little more flexibility, honestly, on how we set things up. Okay, so now we have some examples we're going to do to practice with Pythagorean Theorem. So here is our, well, here's where I wrote that, if you want to pause and copy anything down. Okay, example number 1, we have another triangle. So just a reminder, the C part is special. The one by itself, this is the hypotenuse, which is the longest side. But if you don't have all three numbers, sometimes it's hard to tell where the longest side really is. So instead, what we'll do, we'll find the hypotenuse. How you do that, you look for the right angle, and you go all the way across. So 14 is going to be our C. The legs, the A and the B, are the ones that actually help make the right angle. See how those two actually make the right angle? So those are our A and our B. Now, A and B can flip-flop because we're just adding them. It's not going to matter what order we put them in. I set up my missing one as A. You maybe set up the missing one as B. It really doesn't matter. But we're still going to be using A squared. Here, let's write out. Let's just get in the habit of writing out our formula and then filling in numbers. Okay, so A is the one I'm looking for. I do know the 7 is B. And then 14 is my C. Okay, next step, we're going to evaluate all of those exponents, all those squares. So A squared, we don't know A, so that's still A squared. 7 squared, though, I know is 49. 14 squared, if you need a calculator, go for it, but this is going to end up being 196. Then we'll subtract. We get A squared all by itself on the left and 147 on the right. Now, that gives us the number for A squared, but we just want A. So we need to get rid of that squared, and the way to do that is to use the opposite of squared, which is square root. If we square root something squared, they cancel each other out. Now, if I square root on one side, though, I got square root on the other side. So this is giving us A equals square root of 147. Now, here is the deal. If I don't give you rounding instructions, or if it's not an application problem, I want the exact answer. So here's what we do. Maybe you know all of your perfect squares up to who knows what. Maybe you don't. So if you're not sure, if 147 is a perfect square, we're going to go ahead and simplify this and say A equals whatever that whole number is. If it's not a perfect square, then we're going to leave it just like this, just like it's showing with the square root of 147. So here's what we do. You get out a calculator and you test it. Is this a perfect square? And you find that out by just putting 147, square root of 147. If it comes out to a whole number, that whole number is your answer. If it doesn't, like this didn't, then this is your answer. That's where I want you to stop. So if it comes out to a whole number, great. Use the whole number for your answer. If it doesn't, though, just do this. Okay, so that's our first one. Now, the second one is an application problem. I do want you to round your application problem answers. So we are going to round this to the nearest tenth. In the assignment, I actually typed that part out in the instructions, so you won't have to try and remember. Okay, so with any story problems, especially in geometry where the numbers can interact in a whole lot of different ways, we need a picture so that we can see how these things are coming together. So we've got a ladder. The bottom of a ladder must be placed 3 feet from a wall. The ladder is 10 feet long. How far above the ground does the ladder touch the wall? So overall, our scenario, we need to draw all the objects first, and then we'll figure out where the numbers go. So we have a ladder and a wall. Okay, so the wall's going to go straight up always. We're just going to assume that these builders did a good job, and the wall goes straight up. Then there's ground here, right? Now, if you remember from last unit, anytime we have a ground, like a floor, the grass, anything like that on our story problems, we're going to assume that's level and horizontal. So we do have a right angle here. That's fine to assume that. But there's also a ladder in this story. Now, if I put my ladder like this, if you guys have ever used a ladder like this before, it's just going to fall down, which will be bad news. Hit yourself in the head, make you sad. So ladders always lean against something, unless they're A-frame ladders, and if we ever have that in our problem, it'll say A-frame ladder. Okay, there's my ladder, there's the wall. Now, we do have some numbers, and obviously we need some numbers to be able to solve anything. So the bottom of a ladder must be placed 3 feet from a wall. So here's the bottom of the ladder. There's the wall at the bottom, so that's a 3 right here. Okay, and then the ladder is 10 feet, so my whole gray side here, that's 10 feet. And we want to know how far above the ground does the ladder touch the wall. The ladder touches the wall right here, so we're looking for this part as our missing value. You can use A or B since that's Pythagorean theorem letters. You can use H for height. You can use X because that's your typical algebra one. It really doesn't matter. Now, we do have a right triangle in our picture. Hopefully you see it now. The ladder, the 3 feet to the wall, and up the wall. We have a right triangle. We know two sides. We know the ladder side and the ground side. And we're just trying to find the third. So let's put this together. A squared plus B squared equals C squared. So the C, if this is our right angle, across from that is our 10, so 10 is C. And then the 3 can be A, and the missing one can be B. All right, so we've got all of our pieces put in. There's only one unknown, so this equation is solvable. Let's go. Let's evaluate all of those exponents first. So 3 squared is 9. B we don't know, so we can't evaluate B squared. 10 squared is 100. Now, just like any other algebra equation, we need to isolate the variable, try and get it by itself. So let's subtract 9. We get B squared equals 91. And we don't want B squared, we just want regular old B. So let's square root both sides. That'll give us B equals, and since we're rounding to the nearest tenth, this is not just a test of is 91 a perfect square, this is actually going to give us our answer. 9.53939, but we want to the nearest tenth, so 9.5. And all the measurements in our story were given to us in feet, so our answer will come out in feet as well. Okay, now I don't think that's actually a very safe ladder arrangement, but you can always, if you have a ladder at home and you're curious, there's always a safety thing pasted to the side of it. So you can check and see what it says on your ladder. Maybe that's fine. Okay, one more example and then we'll take a little break and come back for part 2 with the converse idea. So another story, which means another picture. We have a soccer field that's a rectangle 100 meters wide and 130 meters long. So that's an easy thing to put in our picture, right? Just draw a rectangle. 100 is our short side, 130 would be our long side. Okay, now the coach asks players to run from one corner to the other corner diagonally across. So let's say they start here, run diagonally to end here. Okay, we want to know how far they have to run. Now for this though, we do have to remember that rectangles do have right angles. So when we drew this diagonal in here, that running path for the players, we created 2 triangles. You saw that already. But specifically, these are right triangles, which means specifically we can use Pythagorean theorem to find this missing third side. So here's our blue right triangle. We can use Pythagorean theorem to find how far these players had to run. Now, since the right angle is here all the way across, our run distance, that's going to be C. A and B are the measurements from the rectangle. Now, the more you do this, the easier it will get to locate where your hypotenuse is. Because we're going to be finding a lot of hypotenuses, but I can't even say it, a lot of hypotenuses through this unit. Okay, we got some big numbers here. So 1,000 squared, or 100 squared is 10,000. 130 squared, 16,900. I meant to do that in green. And that total equals the same thing as C squared. Okay. Luckily, the adding of that is not too bad because it's just adding 10,000, so 26,900. And now we'll just square root both sides because we want plain old C, not that big crazy one. And this is not, even if this is a perfect square, no one's going to have this one memorized. So calculator it is. All right, 164.01219, blah, blah, blah. But on these application problems, I want you to round to the nearest tenth, which means just one decimal place. So this will come out to 164.0. And our measurements were given to us in meters, so our answer is in meters. All right, great job. Thank you for your patience. Hopefully this was mostly review for you, fingers crossed. But about half of the problems on your assignment are going to use these ideas. So if you wanted to take a break from notes, go do some of the assignment problems, come back for part 2. We'll talk about how to test for whether a triangle is right or not using the Pythagorean theorem in a different way. So thanks for joining me for part 1, and I'll see you soon for part 2.